I'd like to say welcome to engineering and welcome to Eng1020. I am your lecturer for the subject, Lizzie Saronic. Hopefully you've all been onto the Moodle site and had a look around there and seen a bit and learnt a bit about what we are doing. So this week's lectures will be divided into 3 sections. I'll give you an introduction to the course and engineering first. Then we'll jump straight into new material and I'll start talking about loading, to introduce the different structural actions and structural forms to you and the concept of a load path. And then we'll talk all about loads. So hopefully you all know this already. There are 3 contact hours of lectures a week, today and Wednesday, 1 to 3. And the Wednesday lecture will be in here as well. And there are 2 hours of practice classes a week. Unfortunately, they've all been subscribed quite heavily to you, so there is not much movement for changes if you're unhappy with your time. If there's anyone else that wants to change, quite happy for you to do that change that way. But because all classes are full, we can't accept more in other classes. So apologies if you didn't get the class you wanted. If you do have a timetable clash, that's the only time where we will help you find another class time. Okay? Help desks will run 3 times a week. It will start in week 2 or 3, and I'll be putting the notice on Moodle. And hopefully you've already received 1 or 2 emails from me. I'll then email you and give you important information or updates on anything. So please read your emails. Okay? I don't want to get a Facebook account so we can Facebook each other, or I don't want to Twitter you or anything like that. It's not hard to ask you to read your emails to keep up to date and keep in touch with what's going on. My email address there at the bottom, lizzie.saronic. Okay? Email me with any questions. No question is a stupid question apart from what's on the exam. So quite happy to answer questions. I get that one a lot. That's probably the best way to contact me apart from before the lecture or after the lecture. Though after the lecture on today, I'm not that keen because I have to race home to my kids. So if you'll forgive me that, I can meet up before lectures. I'm not in my room all the time, so don't try knocking on my door because I'm only part-time, so I'm not on campus on Thursdays and Fridays. Hopefully we'll be running one of the help desk sessions, so you'll be able to get hold of me. You email me, I'll email you back. Okay? Okay, the schedule, the unit schedule, hopefully you'll learn for all your subjects there is a unit guide for every single subject, and in that guide is all the information you need to know about the running of the subject. In the unit guide, if you don't wish to print the whole thing off, I suggest you print off the unit schedule. So at about page 4 or 5, you'll find a schedule which clearly lays out what week we're in, okay, over here, and then what topic we're covering. So today, as I said, we're doing Introduction to Civil Engineering. A couple of classes have already run all day in terms of practice classes. People had their practice class before the lecture. So you can also see what you're meant to be doing in the practice classes. More importantly here, the schedule will tell you what is due and when it's due. Okay? So that's why I said if you print it off, highlight what's due, stick it to the front of your book, okay? Then you'll be aware of when things are due. This subject is structured such that there's a lot of coursework material in it, so you cannot leave everything till week 10 and learn it all then. The first online assessment occurs in week 3. Okay? Admittedly at the end of week 3, but you'll then be assessed on problem set 1 and 2. So you really can't afford to even miss a week. Okay? If you do miss your practice class, you can just quietly slip into one of the others that run that week, go on to Allocate Plus, see when the other practice classes are on, and when you go in that practice class, just quietly say to the tutor in there, I missed my class and Lizzie said it was okay that I just sat in this class for today. So please don't think, I've missed my class, oh my God, you know, I've missed out on the whole week of material. So download that. References, Well, the Moodle site, of course, where you'll find all lecture presentations, demonstrator overheads will be there, problem sets, project briefs, everything. There is a study guide. There's a folder in there called Study Guide. It's a document that hasn't been modified for a couple of years, but you can use that as another resource for learning the material. The recommended textbook, Hibbler, okay, is just a recommended textbook. If you think you're going to do civil engineering, I strongly suggest you do buy it because we use it again in second year, okay? But you can live without it, but don't tell the book company I told you that. Okay? We don't use the Mastering of Engineering access code. Again, if you do buy it, you can use that access code and go into the book site and do worked examples. Okay? So there's a lot of useful stuff in there if you choose to buy the book. Otherwise, any Hibbler that's an SI edition, okay, would be sufficient. So if you can pick one up second-hand, that will probably do you. Or if you want to live with one without one at all, there are about 5 or 6 copies, I think, in the library, in the Hargrave Library on loan, so you can get them there. But we don't work directly from it. The problem sets are all online, you print them off, and we give you solutions to those. Okay, so how is this subject assessed? We have the exam with 50% here, and as I said, the continuous assessment, a total of 50%. Of that continuous assessment, tests 1 and 2, they're actually not tests, they're online quizzes, we call them. So you will be going into Moodle and sitting those quizzes. Those 2 quizzes are to be done in your own time. You have 5 or 6 days to do them in. You get 2 attempts at them. I'll remind you of this close to the date of the first one. Okay, you get 2 attempts and you get the average of your 2 attempts. I will talk about plagiarism and collusion a little bit at the next lecture with some standard PowerPoints I've been given. Please be careful to you toe a fine line when you work with other people in these quizzes. So we're not saying you necessarily have to do them alone, but it has to be your own work, your own answers that go into them, not someone telling you what the answer is. So they are quizzes for you to do to see if you're up, if you can cope with the material. The third test will be sat in the practice classes in about week 10. That's a closed book test worth 10%. The projects are done in groups of 3, and those groups are chosen within the practice class you are in. So if there are odd numbers, there may be 1 group of 4, okay, but generally, or 2 groups of 4, but generally groups of 3. You will be asked to choose those groups in week 2 and 3, and we hope you'll stay in those groups for all 3 projects. However, if there is a group breakdown, which sometimes occurs, we do allow a bit of movement, okay, for the second and the third project. Project 1, there'll be a bit of discussion in the practice class about what to do, but in one of the lectures I'll explain, I'll give you an overview of what you need to do for the project. Then, if anything is not clear, the help desk is probably the best place to go for help, or ask me before the lecture, or ask your demonstrator in the practice class. Sometimes they may say they're not 100% sure about something and will send you to the help desk. Okay? Project 3, mainly in your own time. So these project groups are actually set within your practice class because project 1 here has an oral component. So there's a 5% of that mark is given towards a presentation and 10% towards a report. And because that presentation is done in your practice class, that's why we ask the groups be formed within your practice class. So it's important you do turn up to your class this week and next week, because this week is a bit of an introduction to get to meet everyone in your class. So it's a very unfortunate when people turn up for the first time in week 4 and go, oh, I haven't got a group. It makes it very difficult for us and also everyone else in the practice class when they have to accept another person and they've already started on the project. So please do try and turn up to as much as possible. I understand if you can't always turn up to lectures. I'm already missing about 50 people which makes me cry. But I'm already missing about 50 people. So lectures are being recorded, okay? To me, it is not the same as being here, because when you are here, you can ask me questions. And I'm more than happy when I'm doing a problem, if you don't understand anything, for you to call out, Lizzie, can you go back a step? Or Lizzie, did you mean to write -10 or +10? So for us to have, for us to communicate while I am giving these lectures, for us to interact. Okay? So prefer you to be here, but if you can't make it, lectures are being recorded. And also if things aren't, if you find you learn differently and don't pick things up very quickly, you can then always watch the lecture as well, online as well as attending. And the exam, the final exam is worth 50%. It's closed book exam. Okay. To pass the subject, do you all think 50% is a pass mark? Yeah, you do have to get an overall mark of 50%, but to pass this subject you need to pass both the continuous assessment and the final exam. So students are required to achieve a mark greater than 45% in the continuous assessment and greater than 45 in the exam, but an overall mark of 50. Okay? So you can get 45% in the exam, and if you get 65% for your continuous assessment, as long as you achieve an overall mark greater than 50%, you're okay. So the hurdle is you still have to get 45% in the exam. You can't get 30% for the exam and 90% for continuous assessment, and it averages out to 60. Okay? So we do that because the exam really is you on your own doing problems without any help, and we believe that that's very important, and you should be able to get at least 45% for that. Any questions so far? So if you get a mark, if you do not get 45 for the exam, the highest mark you'll get is a 45, a fail, an overall 45%. Okay, so that's just a bit of bookkeeping, where everything is, what we're doing, what we're about, and we'll now start on the engineering part. So what is an engineer? You're all here because you want to become engineers, so that makes me very happy. So engineers use math and science to design, build and operate equipment, structures and systems. So I assume you're all good at math and science and physics. Hopefully you have all done physics. Just a reminder, if any of you out there haven't done physics, it is not a prerequisite, but it is very important that you do your foundation physics at least at the same time, because we do assume some knowledge of physics here. Okay, engineers, we're responsible for the existence of our built environment for designing new products and service. We are actually the bee's knees. We just don't sell ourselves very well. Okay? Turning the lights on, electrical engineer. You sitting in this structure, structural engineer. You driving here or catching public transport here, transport engineer. Engineers, everything that's around us is because of engineers. So you should be proud when you become one. So engineers work in teams. We evolve concepts, devise details, control construction and manufacturing. An engineer, a very famous quote by Arthur Wellington, an engineer is someone who can do with $1 what any fool could do with 2. If I asked you to knock up a basic shed, you probably would get there in the end, but you probably put extra material in there or not enough and it would fall down. So we design before we build. A second famous quote is boring. In the yellow pages, when you used to look up boring in the UK, it used to say civil engineers. But that offended some engineers, so that reference is now no longer in the yellow pages because we are not boring. Okay, so as you know, because you looked into all the courses you could do when you came here, well, you probably are not sure what actual branch of engineering you want to do. There are many, many different branches. In my day, there was only civil, mech, electrical, chemical, and that was about it. But now there are far more disciplines around: industrial, mechanical, chemical, material, aerospace, pharmaceutical, mechatronics, environmental, computer systems. You're bombarded with them. So pay attention to these subjects so you can end up doing something that you think you are the most interested in. So why are we called civil? All the others are fairly clear on what they do. Environmental, concerns of the environment. Mechanical, well that's mechanics. Chemical, chemical. Okay, why are we called civil engineers? So the description civil engineer arose from the need to distinguish work performed for the public civil good from that of a military nature. So in the 17th, 16th, 15th centuries, they didn't build things for the people. It was all built for the king or the queen or the pope or the whoever. So we build now for the civilians, okay, for the civil good, which is why we're called civil engineers. So the institution of civil engineers was founded in England in 1818. So before that, a civil engineer did not exist by the name of a civil engineer. So civil engineering itself involves design, construction and maintenance of all aspects of the built environment, not just the environment, for the benefit of the community. So at Monash there are 5 different branches within civil you can look at: structures, geotechnical, water, environmental, transport. So just briefly what they're all about. The pictures really are self-explanatory. So you can come and do civil and not be clear what field you want to concentrate on. So you could end up being a transport engineer where you're looking at highway traffic design, traffic patterns, road networks, rail networks, ports, airports. You could become a water engineer or look at hydraulics and hydrology where you look at storm management. That's been a very popular branch in the last few years, what with the drought occurring and people having to come up with very efficient ways of finding energy and water and using water, minimising the water use. So you look at stormwater management and also water quality, looking at canals and pipelines and river and stream management, the environmental aspect. Geotechnic has to do with everything underground, okay? So foundations, embankments, tunnels, environmental, geomechanics, mining. So there's now a mining degree here I think you can undertake as well. So when we build multi-storey buildings, generally the structural engineers will stop at the ground and then they'll hand the lower part of the building across to more experienced engineers, geotechnical engineers, if it is something like a multi-storey building where proper calculations have to be made. And finally, my favourite, structural engineers. Okay, I like structural engineering the best because it's what we see around us. Okay, so structural engineers, of course, are involved in buildings, bridges, industrial structures, and repair and assessment. There's a lot going on now with retrofitting, improving existing infrastructure rather than pulling it down and rebuilding. So in this subject, we concentrate purely on structural engineering. So we're not going to be looking at the other branches of geotechnical, transport and water, just structural engineering. So what is a good structural engineer? A good structural engineer will create an aesthetically pleasing, I left out of here, sorry, environmental engineers as well, which of course are concerned with protecting the environment by assessing the impact a project has on the air and water quality, soil and noise levels. Okay? So a good structural engineer will create an aesthetically pleasing structure which will not fail in the most economical way. So to be a structural engineer, you cannot just be good at maths, okay? You have to have quantitative, qualitative skills and management skills. So the qualitative skills I'm talking about here is you have to actually be creative. That is if you want to be a good structural engineer, of course. Engineers can have a very bad reputation for wearing grey suits and effectively telling architects, no, you can't do that, you can't do that, no, you can't do that. So we want to breed a better quality engineer here where you're open-minded. So you need to be creative, open-minded. Remember, there's always a solution to a problem. Okay, it may cost more, but you should always be open-minded enough to find solution. You need to be flexible. Now, I can't really teach you those things. Well, in this course, I'm not teaching those things. In this course, we're going to look at quantitative ability. So this, of course, is an understanding of maths and science. So I'm going to teach you about the way we design. And then there's, of course, management skills, which is more to do with leadership and planning and, of course, communication. And you will experience some of this when you are working in your project groups. You'll be working with people you've never met before, and you'll be delegating different tasks to different people. There isn't that much room to be creative in the projects we have, I'm afraid. Okay? But you can be creative in other ways. Now, when I give these lectures, I know they can be a bit dry, and 2 hours is a long time. So what I do is I usually will have a break in the middle of a 2-hour lecture. 1-hour lecture I think you can concentrate on, but what I do tend to do is I put in what I think are interesting things. I just tell you about a structure I like, a structure I've seen I took a photo of. So it's not necessarily a current structure, it's just a structure I think I can tell you something a little bit interesting, you know, that I think is a little bit interesting, that I just like you to tell you a little bit about. And hopefully by telling you about these structures, it will inspire you to become a structural engineer. Okay, so this photo, when you saw on the first slide I had, this sculpture up there, it's called the Angel of the North sculpture. It's in Newcastle, England, and was built in 1998. And I lived in England for 5 years, so I did happen to drive past this when I went back to visit. It's a beautiful structure, I think. Do people like it? Yeah? Okay. It is 20 metres tall and has a wingspan of 54 metres. So that's greater than a Boeing 757. So it's a big structure. So you can see people down here below. Oop. So it's a very, very big structure. It weighs about 200 tonne. And something I want you to start getting familiar with is what weights are, what weights mean. So when I say 200 tonne, I now want you to think that 1 tonne is about the equivalent of a small car. So this structure weighs as much as about 200 cars, and that way you can relate to the loading a bit better. So it's pretty big and heavy. It's Britain's largest sculpture, and it has a very complex construction which required complex finite element computer modelling of it. It has an internal skeleton made from 30mm thick steel. So out here the ribs and the plate here are made out of 50mm and 6mm steel. So just to actually get that in the shapes required a lot of work. So the key to success here was the relationship between the sculptor or the artist and the engineer. So the artist said what they wanted, and the engineer made sure the artist was, could get the result they wanted. This structure, how would you design a structure like this? What's the design load here? The critical design load here is, of course, wind loading. So this structure is up on a hill. It's in between 2 motorways, and it has to withstand winds of 160 kilometres per hour. So there's a lot of overturning moments acting on this. So as well as the structure you see above ground, there is equal depth structure underground that you can't see that makes this thing stand up. So underground, the foundations comprise 700 tonne of concrete. So there's more weight underground, and 32 tonne of reinforcing steel. So they basically had to pile down until they hit bedrock here in order to keep this thing up. The steel it's made out of is called cortine steel, so it's not rusting by chance, it's rusting on purpose. Cortine steel has, I forgot, a higher, lower carbon content, something, but basically it forms this rusty exterior and it forms this rusty skin and then stops, and then so that the rest of the steel does not rust on it. Okay, and that's the Angel of the North. And as I always say at the end of one of my I'll call them interesting facts. If you want to design something like that, you have to know how to do the next thing, which is the really boring maths part of it. But anyway. Okay, so moving on, phases of a structural engineering project. So how does a job like that, Sculpture 1, work? Well, first of all, you get a client request. Client rings up, sits down with either an architect or an engineer, and the client says what they want. So they get a listing of the detailed requirements of the project. And then next comes the concept design. So this bit of scribble here, does that look like anything to anyone? Repeaters don't answer. Okay. Does that look like someone ballroom dancing? I'm not going to dance around the room and make a fool of myself. Can you see a dancer in there? Okay, that was the initial concept design by a very famous architect called Frank Gary, sorry. And this is the building in Prague. It's called the Dancing House. So here is a concept design, and here is the building in its built form. So as I said, you know, you want to work on exciting, interesting projects, you have to be open to everything. And creative and a bit appreciative. See, I love that bit of sketch there and seeing that building next to it. I think it's wonderful. Anyway, in this course we're not going to be looking too much at concept design, but you should be aware of it. The next stage to follow concept design is the detail design. So this is the number crunching, and this is where this subject focuses. So you now have a concept design, how many stories your building has to be, whether they want to, you know, steel, concrete, how big is the block, how big is everything. And then we can start doing, this is when engineers come into their own, we start doing our load calculations, we do our structural modelling and analysis, we choose the sizes required, construction drawings. Now I see people writing things down, all of these PowerPoints are online. So feel free to print them off beforehand and then you can annotate around them. So this is a tablet, which I've only used for 2 semesters, but I can draw, well, sometimes when I get the pen working, on here. So I will be doing worked examples on the tablet, so by all means you can copy them down, but I will be putting inkings online after lectures, so they'll be there to use. Okay, detail design. That's what we'll be covering in Eng1020, load calculations, structural modelling, analysis and choosing member sizes. And once again, you can't just say this member has to be that big. We then have to, very importantly, let me just get this pen working again, come up with construction drawings and specifications. We then have to get the information we come up with into a form that builders and other engineers can understand. Okay? And the final stage is tendering construction. We come up with the specifications detailing what quality and what everything has to be in drawings, and then the job gets put out to tender, and then people then price it based on those drawings and specifications. So these drawings and specifications are actually a vital part of what an engineer does. Okay. But as I said, we're focusing on the load calculations, the structural modelling and analysis and choosing member sizes. So what is structural analysis? This is what I will be teaching you about. Structural analysis allows us to design before building or manufacturing an efficient, economical and functional end product. How do we do it? We use maths. Lucky because we're all good at maths, because that's why we're in here. We use mathematical models of loads and structures, and we predict stresses and deformations and therefore whether failure will occur. So we come up with a mathematical model of reality. It says very often computers will be used. 99% of the time computers will be used to perform the computations. But that is not to say, oh, I don't need to understand or need to know how to do anything by hand anymore. The problem is garbage in a computer, garbage out. You have to understand how structures work, so you understand if the input you put in is correct or is wrong in any way. Quite often in higher years, 2nd, 3rd, 4th year, students go, oh, my computer output's not right. Well, I say that's because you entered something in incorrectly. Well, what did I enter in incorrectly? Well, you should be able to work that out. So it's still just as significant, just as much importance that you understand the basics of engineering, even though the computers will do all the grunt work for you. Okay? You understand the maths behind it. So these structural models, you can actually design a lot by hand. You don't need computers to do your bog standard buildings. That can all be done by hand as it was in the past. So a lot of structures, your standard buildings, square, rectangular buildings, many structures actually comprise a makeup of 2-dimensional structures of beams and trusses. And we can model them in 2 dimensions. So here is a typical 2-dimension model where we represent our beam members and our column members as sticks. So these are beam members, horizontal members, vertical members we call columns. The joint point, how we join them at a joint point, and down the base we have our supports, and I will talk to you about different support types and of course different way to join our members, okay, because you can join them with just a pin, a hinge connection, or you can have rigid jointing. and how the variation, so that is significant in the way a structure will work, whether joints are simple or hinge joints or fixed joints. So this, by working in 2D, we're not just making life easy for us to model, but it's a lot easier to build. If you have a repeating rectangular grid, builders will make less errors. They will build it more efficient, they will build it more economically. And that's what it's about at the end of the day, you know, keeping structure costs low. For a majority of your bog standard structures, you want a cheap structure. Okay, so these models, when you have the bridges, okay, you'll see when you drive home along the freeway or when you're on the bus or on the train, a lot of bridges are just, when you would model this, you would just use a stick model to represent the structural element here. So this beam here, you would just represent with a stick. These arrows down represent the loads. And these arrows up here represent the supports, the reactions from the supports. So what we do is we create stick models, we estimate, we work out how much the structure weighs, we put that as a load on top. We estimate car traffic load in this case, okay, we put that on top as a load, and then we go ahead and we start analysing the structures. Of course, there are many structures that cannot be turned into simple 2 dimensions. So structures comprising complex 3-dimensional forms with complicated loading and material properties, they do usually require computer analysis. So here on the left here we have soil, and because soil is non-linear material, the actual material properties would be put into the analysis, and that would be done by a computer. And over to the right we have a storage bin. It's a 3D structure, so the easiest thing is to actually model the entire thing and then put the loading on there. So when we do so, our elements here are generally not just lines or single elements. They actually are represented by either solid bricks or plates or shells. We won't be doing any of that, of course, in first year. Finite elements is left as a 4th year subject to do. Okay? How are we going for time? Okay, let's just break across quickly to sustainability. Sustainability is, of course, very important. Is this your first lecture? Have you been given these sustainability slides yet? No? Good, I'm the first one. Okay, sustainability, very important at Monash. Most subjects you do in engineering will have a sustainability component to them. Very important in today's environment where we're not doing the world much good living in it. So sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. That's the commonly cited definition. If you look in Moodle, when you look at all your subjects, you should actually see a tab, a Moodle site called, I think, Sustainability. And in that site you will find bucket loads of information that you can use as a guide to other subjects, and when we look at sustainability in more detail in this subject. So I'll give you a 1-hour lecture on passive design in this subject, but otherwise we don't do a lot about sustainability because I'm just teaching you the basic engineering structures that you need to know. Okay, but please do go to the sustainability site when you're in bed and chilling and about to go to sleep and think, oh, I'll click on that link and watch a couple of YouTube videos and become engaged. So there are 3 elements of sustainability: environmental, social and economic. And then we can present them as this Venn diagram here. So the sustainability is the region in the middle of those 3 areas. So what are those 3 things? Well, of course, in terms of sustainability, we have to have environmental concerns. Okay, we have to ensure we're doing well by the environment, but we can't build something that, of course, is not economic. And then as well as being economic and environmental, it, of course, has to meet our social needs. You can't build a building and go, well, it's not good to put aircon in, it costs too much, so we've left it out, and then the people in that building roast all day, and in the wintertime conversely freeze as well. So you have to ensure your building, okay, has a certain standard of living in it, is also economical and is environmental. You have to make sure that it doesn't impact too badly on the environment. So the link of those three regions here in the middle bit, that's what you would define a sustainable structure. So some of you may be doing environmental engineering or environmental subjects, and you'll be learning more about it then. Okay? Why am I telling you about sustainability? Because engineering impacts on all three structures, of course. So engineers, as part of design, we need to consider how to reduce the resources used, how to reduce energy use, how to reduce waste produced, how to improve profitability, because we may have a wonderful structure, but if it's too expensive, no one will build it, and how to improve human use comfort. I'll be, as I said, talking to you about passive design, which is really about going back to how things were done years ago. Do you need an aircon? If you get your windows aligned properly in your house and you can get good natural ventilation in, you may need aircon, but maybe only for half the days of the year, because you can naturally ventilate your home. By siting your building on the site, so the area you're in often, the communal area, has a north-facing sun to it. You can actually, in the winter time, heat up your house without turning heating on at all. So there's a lot we can look at, a lot of ways we can improve human use comfort with reduced cost and less impact to the environment by looking at passive design. So I'll be talking to you about that later. So we know we have lots of sustainable problems. We have climate change, whether you're a believer or not. You should all know about climate change. We know we are eroding soil, air quality, the problems going on right now down in Gippsland are pretty horrific. Ozone depletion, we know that the skin cancer is very important. Resources used, water quality, we've just been through a drought. Okay, these are all problems that we have to deal with, and they all involve engineers. Examples of unsustainable systems, well, private transport system. How many of you drove here today? How many of you could have caught public transport but drove? Yeah, okay. So, you know, but if there are ways of improving public transport, then maybe more people will go that way. Fossil fuel use, we have to move away from coal more. Why aren't we putting more panels on the roof? Costs too much. But, you know, so it's very important that you can weigh up the environmental and the social and the economic cost here. And, of course, waste treatment and disposal. Okay, looking at environmental issues. This building, have you seen this in the city? Yeah? Great structure, I think. Do you like it? Again, I show you stuff that I think is beautiful. I think that's a great looking structure. What's behind there, I don't know a lot about, but the outside skin I think is stunning. In actual fact, the hub has a large number of, you'll hear this term a bit, ESD features. And ESD stands for mentally, and I'm not the neatest writer on these things, I'm afraid. I will try and do my best. Sustainable design features. So it does incorporate strategies of water, waste, recycling management that are the equal of any ESD-focused buildings on the planet. But I just want to talk about the outer skin. So the outer skin comprises automated glass sunshading cells, which rotate, can be individually rotated to be exposed to the sun as much as possible, and thus when they are exposed to the sun, they're obviously creating shade behind them. So it's a way of naturally shading the building while still letting light into the building. So the lighting in the building, the lighting requirements in the building are not so high, and the heating and cooling requirements in the building. So I say it can rotate to expose these cells to the sun as much as possible. In the winter time, they can also be rotated to allow the sun to come in to heat up the building. If you do get a chance, pop in the building and wander around. There's this great light coming in. They've got their corridors on the outside area, and the light that comes in is actually quite beautiful to look at. Now, these cells, again, it's an environmental building, but sometimes there's technology, well, I mean, there is research out there that can't be put into place yet. So these cells have been designed so they can easily be replaced as advances in the development of solar power result in improved technology. These have been designed so the glass can be removed and solar panels can be put into each cell, thereby the building will be producing its own energy as well. So that's just a potential future. Currently no solar panels are installed, but it has the capability to accommodate that technology in the near future. So have a look. I particularly like the different materials, the glass and the steel versus the brickwork. So have a look next time you're in the RMIT Design Hub. Okay, we'll go another 10 minutes, and you all alive still? You're all okay? Is it warm at the top? No? Okay, cool. I hope you appreciate these windows have been put in. This is all newly renovated to create a better learning environment for you. So you can't go to sleep in the back row now, it's all light. Okay, so part 2 now, we'll start today, we'll continue and finish off on Wednesday. The objective is to understand the concept of a load path, to describe 4 structural actions and to describe different structural forms. So, what is a load path? It's a route along which the applied loads are transferred to the support. So, in your current situation sitting here, your load path, the weight of your body, of course, passes into the seat. There are no chair legs here, but the weight of your body is being transferred through the nuts and bolts into the building. Assume you are sitting on a chair with legs into the chairs. It then goes into the floor. If we were, well, you're up on a raised floor there, but if you assume you're all on a higher level in a building, it goes from the floor into the walls of the building, then into the footings, and then into the earth, into the ground. So an engineer's main responsibility is to ensure that no failure occurs along the load path. So here we have our wonderful Flinders Street station. The load path here when you're looking at the roof structure. Okay, if we had a bird or someone walking up here on the roof, what's the load path here? The person would be standing, say the person's standing above it here at this point. So the roof sheeting would transfer the loads to our purlin members here. These are called purlins, our secondary members. And these secondary purlin members then transfer the load into our primary truss. And then from the truss, transfers down to the column and into the ground. So there's the load path there. So we don't need arrows to explain it, just a continuous path to follow. So that's what a load path is. And when you do your practice week, you'll be asked to use the concept of a load path to explain in a case study case why one structure fails and why the structure actually failed, killing 114 people. Okay? Now, the process of load transfer involves structural actions. So now we're going to learn a bit of engineering terminology, of which there are 4. Axial tension and compression, that's pretty well understood by the layperson. You squash something, okay, you are compressing the seats, the padding on your seats at the moment. The other way, when you stretch something, when you hang from a rope, the structural action is tension. Most structures don't transfer load by structural actions of compression and tension. They do so by the structural action of bending. So beams bend. So when you walk across a plank or a bridge of any form, okay, the bridge is bending. And there we have a fishing line. The load is pulling down. So you could say our rope here is in tension, has a structural action of tension in it, but our fishing rod itself is bending. The third structural action is shear, which is very hard to actually see, but shear causes distortion. Shear is the internal action trying to slide one part of a beam over another, and it causes distortion. So when we look at these structural actions, they actually have an equivalent structural form, so I'll talk about that in a minute. I have a very poor image here because I couldn't find any better, of a building after an earthquake hit. okay, where the entire building sheared sideways. So shear forces generally occur with bending. They go hand in hand with bending, and of the two actions, bending stresses are the more critical. We're going to do quite a bit of work on bending stresses, less on shearing first year. The third structural action is torque, and I didn't bring my ruler, but I just want to now just mention the difference between bending and torque. I think in physics, all bending you refer to as torque, okay? Torque is the twisting, okay, creates twisting, and it's bending about the longitudinal axis of a member. I should have brought, you'll see me bringing in flexible rulers and bits of foam to try and actually show you how things move. So torque is the fourth structural action which causes twisting. So here's the deformation mode form for each structural action. As I said, in compression, you know something squashes or it shortens. In tension, we know it stretches. When something is experiencing bending, it curves. In shear, maybe not so obvious, but shear causes distortion and torque causes twisting. So please stop talking about bending and referring to bending as a torque now. If something is curving, we say it is bending. So common structural forms around us are made up of arches, beams, trusses and cables in the two-dimensional forms, and the three-dimensional equivalent shells and domes are what an arch, you would call an arch in 3D. Beams, we have slabs in 3 dimensions. Trusses, we have space frames and cables and become membrane structures. So these structural forms can be defined by their structural actions: tension, compression, bending, distortion, torque. So arches experience compressive forces in them. Beams, well, we know beams bend, so they experience bending and shear. Trusses, when you actually look at the individual truss members, they transfer load by tension and compression by axial forces. And cable structures, I think you all know how cable structures transfer load, just by tension. You know, if you turn a cable structure, is basically think of it as a bit of rope. You can't squash it, you can't compress it. So I will now look at each of these structural forms in more detail. So starting with arches, not so many arches built today. Lots of arches built as far back as Mesopotamian times, 2000 BC. Why were there a lot of arches built then? Well, because the building material, they built out of whatever they had around, and they had a lot of brickwork and they had a lot of stonework. And because arches transfer load through compression, we know when you build something, you can just pile it on top and on top and on top and compress it, okay? So because the only action is compression, stone and mortar and brickwork can transfer that easily. So structural action is compression with a bit of bending. Our vertical loads, applied loads here, are turned into our radial compression forces here, which are then reacted by the supports. So I think everyone's heard of the centre stone being the keystone here. It has the name keystone, but it actually does not perform any other action as all the other members in an arch. So arches are nowadays not made out of stone necessarily. Here we have a beautiful, beautiful arch bridge built in 1929-30, made out of concrete. Chadstone Shopping Centre, though apparently I'm not allowed to take photos at Chadstone. You'll see everywhere, do not take photos, so don't tell anyone I did. Chadstone Shopping Centre, the main walkway, the skylight area is made up of arches, so these steel members here are being compressed in, and there will be a bit of bending on there if the wind blows from one side, okay, but primarily the load here is self-weight, and that will be creating compression forces. And here New Wembley Stadium in London, where you have this big arch here, the arch itself is made up of trusses within it, but there is an arch structure here which is picking up through these cables, which is picking up the roof structure through the cables there. Beams are the most common structural form. Simplest beam here, just a bit of stonework across a river. So it didn't take any rocket science to design a beam. Someone wanted to cross the river and they found a big enough slab and they put it down and They went ahead, the beam cracked, the rock cracked, so they just put some support rocks closer together and got to a point where they could cross the river without getting their feet wet. So the structural action here is bending with a bit of shear, and as I said, beams are the most common structural form. Then we have trusses. Here we have Bunnings Superstore. Look up next time you're in there buying paint or something, where our purlin members here are beams, but our main members here are trusses. Trusses are triangulated structures. Anything that's triangulated, we call a truss, and they are efficient for large spans. When the span gets bigger for a beam, in the end it starts bowing, deflecting too much, and at that point you would consider putting in a truss in its place. A truss is a stiffer unit. Here we have the walkway over Blackburn Road. Pull up the car and have a look at it if you want. It's a simple truss structure. It's one you would be able to design by week 5, because that's what you're going to be doing. By week 7 you will have designed a truss structure similar to this footbridge. Our final structural form are cables. So cables, usually a group of metallic ropes blended together, or it could just be rope used in suspension bridges and cable-stayed bridges. See, a suspended bridge is over here where the bridge is being suspended, and cable-stayed is where the cables come out from a point to pick up the beam along the way, the bridge. Cable structures are very efficient structural forms, okay? Very, very efficient. However, they change shape. They're unique in that they change shape as the load changes, so they always stay in tension. And this we call funicular. What do I mean by the shape changing? Okay, if I have this bit of string here and I have just a load in the middle, I get this triangular shape. However, when I start moving the load out, it actually changes the shape of the structure. So you can't have just a bit of cable to support a road, because the road will move around too much. That's why we have cables up here, and then we would have a stiffer deck below being picked up. Okay? We'll stop there.